morning, happy Wednesday, happy last Wednesday of the semester, happy second to last day of the semester, happy second to the last day you have before you turn anything in that's late. Your either or labs are due today by the end of the day. How many of you, well, if you plan on turning those in today here, we would like to accommodate that, but if you're going to do that, we're going to ask that you write your mod number on top of the lab page, front page of your lab. Obviously, you're going to have your tour on there already, so it may say Gussie, but you should write Gussie 1314 or Neubauer 56 or Blackford 12, whatever the case might be, but please write both your tour and mod number on the front page, top of your lab. Due today. As I mentioned at the beginning, all late work due tomorrow. If you have labs that haven't been turned in, if you have worksheets that haven't been turned in, if you have tests that haven't been taken, and as hard as it is to believe, there are some of you that even have multiple tests that haven't been taken. Those are a significant percentage of your grade. They will become zeros at approximately 2:55 tomorrow if they're not taken. They have been in the Resource Center since the day, or the day, possibly the day after the test was administered. So if you haven't taken it, it's because you haven't chosen to take it. This Gage.
When can we turn in like the late passes? Or like
Late passes just turned into the
The yellow those are only for first semester, so if you don't hand those in, if you have 0 missing assignments, you still have that. Like, oh, I already have used mine. Great, you utilize it. But if you did not have any late assignments, it's a reward. Make sure your name is on it, you need to put that in our slots. If your name's not on it, we are not going to try to figure out who the heck it belongs to. That'd be impossible to imagine. So. Last little item on that, sorry. If you have like a 5-point, I've been getting a few of those, like the blue from the bingo, like 5 points homework. That has to be stapled to a homework assignment. That has to actually exist with something. So then if you attach to a homework assignment, that doesn't have to be this semester, it can be next. Those are all unlimited then. If it was a 15-point assignment, it would become 20 out of 15 if you got all the points in the first one. So just hand those inside.
All right then, moving on. Today's plan is to introduce empirical and molecular formulas and how to determine or how to figure out empirical and molecular formulas for compounds. This is going to be an extension of what Mr. Neubauer did last week with percent composition. So as a startup, as kind of a warm-up, we're going to do a percent composition problem and roll right on into empirical formulas and molecular formulas. So let's get you up. This is very funny. This is, I think you can read it. You can see there's all the elements: carbon, aluminum, silicon, oxygen, nitrogen. So it's fun. It's not nearly as funny if I have to explain it, but it's this book. We have all the elements of a first-class thriller. Elements. Okay. So now we're going to calculate the percent composition of MgCO3. For those of you that did your own work on the nomenclature unit, you'll know that this is magnesium carbonate. Magnesium carbonate. How do we find percent composition? First, We want to find the whole. What's the mass of the formula? The formula mass, the mass of the whole darn thing together. Yep, there's a spot for this right on your note-taking sheet.
Oh, I'm sure it is. I did.
For those of you that are ahead of the game, I've already written this down. By all means, you could proceed and find the percent magnesium, percent carbon, percent oxygen. Or you can just look at me and wait for me to click the button. So to find the percent magnesium, we're going to identify the mass of magnesium. Well, we already did that. 24.31, we're going to divide it by the whole mass. 84.32, and we're going to multiply by 100. 22 different people talking. So your percent magnesium, 24.31 molar mass of magnesium divided by the formula mass, multiplied by 100. Part divided by the whole times 100. 28.83% of that compound's mass is magnesium. Which means if we had a 100 gram sample of magnesium carbonate, we had 100 grams of this stuff, 28.83 grams would be magnesium. Carbon. And you don't have to wait for me to do the next one. And if you've already done oxygen, I'm confident you've got 56.93% oxygen. So this was last week's worksheet. You did 20 different examples of it. Maybe not 20. Maybe embellishing. That might be hyperbole. I really don't know. Does anyone have any questions on percent composition? What you did last week? Good, because that's what we're going to do, or that's what we're going to use to move forward into empirical formulas. When you do your percent composition, we want to make sure that we're keeping track and using plenty of decimals. Don't round, because if we round, then our percents are going to be rounded, and then when we add them up, we might end up with 96% or 102% if we're rounding. So please keep your rounding to a minimum. If you got 99.9 or 100.1, that's probably okay, but we don't want to round significantly. Here we go. Two different types of formulas that we're going to be looking at today are empirical and molecular. Empirical is the lowest whole number or the simplest ratio of atoms in a compound. Sometimes these compound formulas that are given, that are true compounds, can't be simplified anymore. Sodium chloride, NaCl. There's one sodium, one chlorine. You can't simplify that down. It's just NaCl. H2O. We can't simplify that down and still have whole numbers for our subscripts, which is what we need. The molecular formula is the true or the actual number of elements, or the actual number of each type of atom in a compound. So So in a water molecule, there actually are 2 hydrogen atoms bonded with 1 oxygen atom in every water molecule. You're familiar with that formula. You may not, probably aren't familiar with the formula for hydrogen peroxide, which is H2O2. There actually are 2 hydrogens bonded with 2 oxygens, so there's 4 atoms that are bonded together in peroxide. But if we were to simplify that down to the empirical formula, and that's going faster than I wanted to, H2O2, there's 2 hydrogens for 2 oxygens, which means it's a 1-to-1 ratio, so we could write HO as the empirical formula for hydrogen peroxide. And you'll see several examples. So the relationship between the molecular formula and the empirical formula. The molecular formula is the empirical formula multiplied by some constant, n. And an example of that, C6H6. We could write that in this format as open parentheses CH, close parentheses 6, where we would distribute the 6 throughout and get this. So our empirical formula is the lowest whole number ratio of atoms in a compound. This is a 1-to-1 ratio, so our empirical formula would not be CH in parentheses with a 6, but rather just CH. Everybody down with that? Good to go? Alrighty. Your ionic formulas, and this is already on your note-taking sheet, your ionic formulas are always empirical. They're always simplified down to the lowest ratios. Sodium chloride, magnesium chloride, MgCl2, we can't simplify that down and still have, we could have half of magnesium for 1 chlorine, but we don't want fractions in our subscripts, so in order to keep our subscripts as whole numbers, that's as simple as it gets. The molecular formulas sometimes, as I mentioned, might be the empirical formulas, but oftentimes they're not. So for example, water, H2O, can't be simplified down any further, so the empirical formula is the molecular formula. Can we simplify C6H12O6? You betcha. Do it, please. How simple does that one get? CH2O. Very nice. And C12H22O11. Not so much. So that one's going to be as simple as it gets. All right, let's flip her and show you how to do it. So we got a few basic steps. The first thing we want to do is assume, and I mentioned this previously when we were doing the percent composition of magnesium carbonate, we want to assume that once we've determined the percent composition that we have 100 grams of it. So you can replace your percent with grams and convert to moles. That's what all this says, is replace your percent symbol with grams and convert it into moles. You're going to do that for each of the elements in the compound. Once you've done that, once you figured out how many moles of each element there are, you're going to identify what's the smallest number of moles and divide all your values from step 1 by that smallest number. And then finally, step 3 is a maybe step. It's also kind of a baby step, but if after you've divided all these numbers, your result are all whole numbers, then you won't have to do step number 3. But if some of your ratios of moles divided by that smallest number of moles is something other than a whole number, then you're going to have to find some common integer that you're going to multiply all of your values by so that they're all whole numbers. And that'll make a lot more sense once you see it, if that doesn't make a lot of sense yet. So we're always doing 1, we're always doing 2. Sometimes we're going to do 3. So here's the example we're going to walk through together. Adipic acid gives you the percent composition of each of the 3 different elements in it. We've got carbon, oxygen, hydrogen. There's 49.32% carbon. Notice how we got a couple of decimal points. We're not just going to call that 49%. We got 43.84% oxygen. Keeping a couple extra decimal points. 6.85% hydrogen. First thing we're going to do is replace. We're going to assume that we have 100 grams of this stuff. Replace your percentage symbol with a gram. So we treat our percent as mass and convert our grams to moles. So the first one, instead of 49.32% carbon, we got 49.32 grams of carbon. And we haven't done a lot of this conversion real recently, but you'll quickly be reminded of how we do it, and we'll do it a lot now. So there's 12.01 grams of carbon in 1 mole. Again, don't just write 12 grams. And that gives us 4.107 moles of carbon. And we'll do the same for hydrogen and oxygen. So our 6.85 grams of hydrogen, because it's 1.01 grams per mole, is very close to the same value, but 6.85 becomes 6.78. And our grams of oxygen converted to moles becomes 2.74 moles of oxygen. That's step 1, finished. Assume we've got grams instead of percent, converted into moles. Step 2, we're going to identify the smallest number of moles, 2.74. And we're going to divide all of our other values by 2.74. So carbon, 4.107 divided by 2.74. Same with hydrogen, 6.78. divided by 2.74. That's not a whole number. We can't have 1.5, we can't have C with 1.5 as a subscript and H with 2.5 as a subscript. And obviously, if we take our 2.74 moles of oxygen and divide it by 2.74, that ratio is 1.5. It's not 1.5, it's 1. That's a misprint. Sorry. But that'll be a very funny joke for the next 10 or 15 minutes. You just wait.
Wait, is this supposed to be just?
It's 1.
That's supposed to be 1. That is a misprint. 1. That's 1. Whoops. That's me backing up. So 2.74 divided by 2.74 is not 1.5. It's 1. See? It's 1. So this is our third step that we sometimes wouldn't have to do. If in that previous step we had gotten all whole numbers, we had gotten a 3 and a 5 and a 1, then our empirical formula would be C3H5O1. But we didn't get that. We have 1.5, 2.5, and 1. So we need to come up with a number, an integer, that we can multiply all of these numbers by, that will give us all whole numbers. So they're all going to get multiplied by the same number. Because these are halves, you take something in a half and multiply it by 2, it's always going to give us a whole number. So 3.5 times 2 is 7, and 4.5 times 2 is 9, etc. So in this case, we're going to multiply all these by 2. Now, we've got our ratios of carbon, hydrogen, and oxygen in the simplest whole number ratio. So for every for every 2 oxygens, we're going to have 3 carbons and 5 hydrogens. So that is our empirical formula. That's as much as we can simplify it down. Might that be the actual formula? Question mark?
For hydrogen, wasn't it 2.47 and now it's 2.5?
Yes. Yep, this was 2.47 on the previous screen, which is very close to 2.5. You can do some rounding. If we had 2.25, you wouldn't want to say that that's 2.5. If you had 2.66, you wouldn't want to say that's going to be 2 2/3. But the fact that it's very close to 2.5, we're going to go with 2.5. And you'll see as you do a number of them when you're going to be comfortable rounding and when not. So this may very well be the molecular formula. We don't know that yet. How would we know? Well, we could check. That's what we're going to do next. Check the molecular mass of adipic acid, which you could look up, but for your purposes in this class, we're going to give it to you. So this is how we're going to figure out if our empirical formula is the molecular formula. So if we tell you that the molecular formula of adipic acid is 146 grams per mole, we're going to compare that to the mass of the empirical formula. If they're the same, we're done. If the empirical formula, C3H5O2, gives us a mass of 146, then that is the actual formula. So that's the first thing we're going to do. In step 1, we're going to find the formula mass of C3H5O2. So 3 carbons, 3 times 12.01, plus 5 times 1.01 plus 2 times 16. So how does our molecular mass of 146 compare to our formula mass of 73? Clearly it's different. And you might even be able to recognize just, and if you can't, that's fine, because you're going to do the next step regardless, hopefully. But the next step is to find out what the ratio of the two masses are, or is. So we're going to take our molecular mass and divide it by our formula mass. So the actual mass divided by the simplified mass. So 146 divided by 73 is going to be 2. And even if you did 146 divided by 73.08, you're going to get 1.98 or 1.99, something like that. So it's 2. Which means that our actual mass is twice as much as our empirical mass. What do you suppose that means in terms of our formula? It's wrong, but it means we need twice as many of the stuff that we figured out. So we're going to multiply. This is the last step of finding our molecular formula. We're going to multiply our empirical formula times 2 in this case. Multiply your empirical formula times the number you get when you take the ratio of your molecular mass divided by your empirical mass. So if you recall from earlier when we had empirical formula times n, that's n. So that is the molecular formula for adipic acid. It seems like a lot maybe, but it's really just several simple steps. So we are going to, as soon as we give you an opportunity to ask questions if you have some. Then we are going to get you better at this.
little barbecue sauce.
All right, is everyone hooked up? Okay. We need practice with the skills that we just used. So we are going to take advantage of the misfortune of others. I don't know how many of you have heard about this or saw this in the paper, but it's a sad day in Moleville, home of Mole Airlines. If we could all just have just a moment of silence in memory of our victims. Thank you. There was a crash, and there were several.
What if you're a mentor for the students?
Well, clearly you're not sensitive to the families of the victims. How many of you are preoccupied with your tour rather than the feelings and the empathy for the victims right now? Yes. In answer to that, yes, in answer to that question, please put your new tour. So, ladies, gentlemen, you have a week. You have a week to figure out who your new tour is. Please, please. So what we want to do is, in an effort to help the families of the victims, we want to analyze the different chemical samples that were found on the victims. And, well, you probably haven't had an opportunity to read this yet, but not only were there victims of the crash, but there may have been a murder. So we would like to employ our background, our knowledge, our wisdom in chemistry, percent composition, empirical and molecular formulas, to bring some closure to the families of the victims. And I would like to help you, because I too want to help the victims and their families. So if you look at this, on the bottom of the front page there's a number of victims pictured there. Gives you just a little bit of background knowledge for them. If you flip the page, pages 2 and 3, and actually 4 as well, you'll see that there are a number of post-it notes that correspond to the different passengers. And the chemicals, the substances that were found on them, it identifies whether they were found in their blood, in their stomach, on their hands, etc. So what we need to do is to take the chemical compositions of the substances that were found, identify what the molecular formulas of those substances are, relate them back to the different passengers, the different victims of this tragedy, and put the pieces together to try and figure out who is our cold-blooded killer? So I think the best thing to do is to get started. Alrighty, if you would please flip to page 2. Yep, okay. Here's a question. Boys, girls, your question is, why are there multiple Post-it notes for the same passenger? Okay. In some cases, yeah, for example, passenger B had 2 different substances found. So they're not different passengers, they're different substances that are found on the same passenger. For passenger A, there was only 1 chemical substance found, and that's going to be the first example that we're going to do. So I know this isn't very clear, but you have it right in front of you, and it's nice and clear for you to see on the screen or on the sheet. We want to take our chemical composition and determine the molecular formula. So our first step is to assume that we have 100 grams of this stuff. So right away, where it's percentage, we're just going to put a G over that for grams. Step 1, assume we've got 100 grams. Step 2, convert grams to moles. So if we got 67.31 grams of carbon, how many moles of carbon is that? Well, there's 1 mole of carbon for every 12.01 grams of carbon. Grams of carbon are gone, and I have these already done for you. 5.604 moles of carbon. And we'll do the same thing for our hydrogen, nitrogen, and oxygen. You can do it on your own, or you can do it with me. 1 mole of hydrogen for every 1.01 grams of hydrogen. Get rid of our grams, and we've got moles of hydrogen. There's 6.911 of them. Again, keeping a lot of digits. I'm not going to call that 5.6 and 6.9. Nitrogen. For every 1 mole of nitrogen, we've got 14.01 grams. That is 0.3298 moles. And for oxygen, for every 1 mole, 16 grams. And that's 1.319 moles of oxygen. I heard you. Next, we're going to divide all these by the smallest. So our smallest value is 3.3298. So obviously 0.3298 divided by 0.3298 is 1.5. Right, 1. See, that's very funny. 1. And when we divide the others by our 0.3298, you're going to get about 17. Very close to 17. Very, very close to 21. And for our oxygen, very close to 4. So we don't have any halves or thirds or fifths. We've got all whole numbers. That's a sweet deal. That means we don't have to do step number 3, which is find some integer to multiply them all by to get them into whole numbers. So our formula, C17, H21, NO4. Flip to the back page to cross-reference that with cocaine.
Suspected
See, that's easy, right? You can do that 15 more times, right?
Now your job's not to guess who it is yet, because believe it or not, there are some twists and turns in here. So you don't just look at them and go, oh, this person's this profession or whatever, and just assume immediately. There's more to it. So I would not fill in any names until you've done all the post-its. It says it on the front.
We have to gather all the evidence before we can put the pieces together.
How do you get the 5.6 on the top?
That was from the 60 whatever percent divided by 12.
There's like the top number.
Yeah, it's the 60. You're taking this times 1 divided by 67. All right. Good news. We got time for another one. All right, this is passenger B. And it's the second post-it note for passenger B, the second sample for passenger B, the one that has 46.66% carbon. We're going to use the same process we just did. Replace our percent with grams. Because again, we're assuming that we've got 100 grams of it. If 46% of it is carbon, then if we've got 100 grams, 46 grams of it's going to be carbon. We don't want to round it to 46 though, so we're going to stick with 46.66, and we're going to convert that into moles. 1 mole for every 12.01 grams. 1 mole for every 1.01 grams. 1 mole for every 14.01 grams, and 1 mole for every 16 grams of carbon, hydrogen, nitrogen, and oxygen, respectively.
Guys, in case you're wondering, in those T-charts, what Mr. Blackford's writing, it has to be those molar masses. If you just rounded to 12, 1, and 14, there are a few that will not work. And it's like, well, that's so small of a difference, just, it won't work.
Yes, don't take shortcuts. That'll just make your life more difficult. And then again, it's been a while since we've done these, but hopefully we're reminding you how simple this is. We've got grams times mole per gram, so our grams are going to cancel. You're going to have 46.66 times 1 divided by 12.01. That gives you 3.5. Sorry, not 3.5. 3.885 moles of carbon. 4.436 moles of hydrogen. 2.22 moles of nitrogen, and 1.11 moles of oxygen.
Does it matter how far we go with the, like,
More is better. We're not telling you gotta go 5 digits beyond the decimal, but I would go at least probably, it'll kind of be determined by when you plug and chug with your calculator, but I would go on average probably at least 3 digits. 1.11 is our smallest, so we're going to divide everything by 1.11. So 1.11 divided by 1.11.
5.
Thank you. Just never gets old. 2.22 divided by 1.11. 2. 3.885 is about 3.5, and our hydrogen is about 4.
I did this one myself.
Now, in the previous example, we had all whole numbers, so we didn't have to find some number to multiply all of our ratios by to get them into whole numbers. This one, we've got a half in here. Easiest way to get rid of a half is to multiply by 2. So that's going to give us 7, 8, 4, and 2. C7, H8, N4, O2. Once you've identified what your molecular mass or molecular formula is, you look on the back sheet, find that formula, and the corresponding name. Thiobromine, which by itself probably doesn't mean anything to you.
Flavor.
But that's chocolate flavoring. So clearly that's going to be the dentist.
You never know.
No, you don't know. That's what I'm being sarcastic. Kidding. So again, as Mr. Gussie already said, don't just jump to the immediate conclusion that you know who somebody is just because of one piece of evidence. Put everything together and then start to solve this brutal, tragic murder. Yes. You got 5 minutes left. You can probably do at least one more.